Hi, vintage computer friends. Today we have the Microprofessor MPF-1B again on the bench. My last video featuring this very nice 1981 Z80 CPU trainer was 2 years ago or so, right? And I figured it's about time that we do something again with this very nice machine released by the company Multitech, nowadays known as Acer. And what I wanted to bring to your attention is that software development for this machine has now become incredibly comfortable and easy and straightforward. And this is largely due to PicoRAM 6116, which is my expansion board for the microprocessor. It's an SRAM emulator, right? So it plugs into the 6116 SRAM socket on board of the microprocessor, and then the Raspberry Pi Pico is emulating this RAM. And it's also equipped with an SD card interface here, so you can actually load and store whole memory dumps right from and to SD card. And of course you can also then use a Z80 assembler on the PC or Mac, produce a hex file there, put it on the SD card, and then simply load that program into the microprocessor. You don't need to enter the machine hex codes using the monitor anymore, right? So that's what PicoRAM 6116 is doing for you. And it also offers multiple banks of memory, right? So here we have bank 1 is serving this clock program currently, right? And I can simply swap the bank, right? So here's a counter program now, and the machine of course crashes then basically because I'm hot plugging the RAM or the program basically, right? So, but let's run this program now in bank 2. Yeah, and I featured this program, in my series of videos about the microprocessor, how to program it, right? That was one of the demos there. And then here's another program, an egg timer. So I think you set the number of minutes here that you want the timer to run. Okay, and then it just does a countdown, right? So yeah. And of course these programs are just, as hex files on the SD card. So what I want to demonstrate to you today is how to write the, we are using the Towers of Hanoi again, the recursive version of the Towers of Hanoi, and use a online web assembler to compile the hex file for it, right, and then run it on this machine. Alright, so let's implement the Towers of Hanoi for the microprocessor MPF-1B. And I'm going to use assembler, Z80 assembler, right? And a great online assembler is asm80.com that you can see here. Not only does it support Z80, but also 6502 and x86 and so on, a whole bunch of different 8-bit CPU architectures. So great stuff. And as a blueprint, we are going to use a version of the Towers of Hanoi in the Z80 code that can be found on the site rosettacode.org, which basically has the Towers of Hanoi listed for all kinds of different programming languages, right? And there's also a version for the Z80 assembly here, which is running on CPM 3.1. But yeah, that was uploaded 2023 by XORF. Thanks for that. So we're using your program as a blueprint here, and all we got to do is basically get rid of the CPM specific calls, right? For example, the BDOS calls that write a string to the console and so on. That's going to be different on the microprocessor. But other than that, it's straightforward, especially since the Z80 has a proper stack, right? So we can use push and pop for registers. We have plenty of registers, and hence there is really no trouble implementing recursion on such a CPU. So unlike the struggles that we had with the science fair microcomputer trainer, for example, or the Bush Microtronic, right? So the instruction sets don't support stacks natively, and so you have to do a lot of hackery in order to get that running. So if you're interested in that, check out some of my other videos which have implementations of the Towers of Hanoi for these very restricted CPU models. So, but here we have the Z80 and everything is easy basically. So just a note here that the program is structured a little bit differently. In my previous implementations of Towers of Hanoi, we basically used this function here as a blueprint, right? And that basically had an inductive case for the disk number 0 or 1. Then it only outputs the move, right, from source to destination of this disk. Else, for the inductive case, it does 2 recursive calls, right, for the reduced disk. And in the middle, in between those calls, it produces the output, the instruction for how to move the disk from where to, right? And so the program that is on Rosetta code here, which we are going to use as a blueprint from XORF, uses this basically as a blueprint, right? So there is no else statement in this if, and it's a little bit more efficient, so to speak, right? So basically what it does is for the recursive case, it works exactly the same as the previous program, right? So it does a move in the middle, but then if 1 is reached, right, and the program still makes a recursive invocation with n equals 0, right, and that immediately returns then, because the whole code is guarded by n greater than 0, right? So in that case, basically for n equals 1, we will get basically a no-op here, right, and then the write instruction, and then another no-op recursive call. So this makes more recursive calls basically, right, but is an even more succinct, implementation of the algorithm, so to speak. And given that we have plenty of memory space now, having a few more stack frames basically, and a few more recursive calls while running this program also isn't an issue. So that's basically the pattern after which this code here is modeled, right? But now let's get started and see how we can implement this for the microprocessor. Okay, so let's start at address 1800, which is the default address on the Microprofessor MPF-1B for programs. And so when the Anoi program starts up, the first thing we want to do is make a beep on the loudspeaker. So we are calling a firmware routine here, tone 1, which produces a 1 kilohertz beep, and you can specify the duration in the HL register pair. So this is something like 200 milliseconds or so. And then we want to make the main call to the Anoi function with the parameters that we supply. So we want to use it for 3 disks here. So the number of disks is in the accumulator A. And then we are using A, B, C in the B, C, and D registers for the source, target, and spare pack. And those are just the pack names, right? A, B, C, like in our previous implementations for the other machines. Just hexadecimal numbers for those, and those print nicely on the hex display of the microprocessor then. Okay, and then we make now that we have prepared the arguments for the first recursive call, we make the call, and then when that call returns, we make another beep on the speaker, so we know that the program terminated properly. And tone 2 does a 2 kilohertz beep. And again, it's 200 milliseconds, and then the program halts. The microprocessor has a very nice halt LED, and that way we know the program executed and terminated properly. So how does Hanoi look like, right? So let's have a look here. So here's a nice comment, right, also from the original Rosetta code version here from XORF, right? And so it moves A disks, the number of disks is in A, from B to C via D, right? Source, target, intermediate. And remember in this program here that if n equals 0, then a call to Hanoi with n equals 0 returns immediately, right? Because it only does something for n greater than 0. So we do the test here if the number of disks is 0, right? If the accumulator is 0, then we want to return immediately. And here's an old Z80 programming idiom. To compare the accumulator for 0, you can do an OR with itself, right? OR A. And then if that's still 0 after the OR operation, then obviously you had a 0 in the accumulator in the first place, and the 0 flag is set, and then you can return here if 0, right? Set is 0, flag is set. Else we are now ready, n is not 0, the accumulator is not 0, then we have to make the first recursive call now. And for this we just push everything on the stack. So good that we have a proper stack this time, right? And push all is a macro. It simply pushes A, F, B, C, D, E, H, L, or Z 16-bit 2 times 8 register pairs to the stack, and pop all, restores them from the stack. Of course in reverse order because it's a stack. So, and we have to, of course, decrement A now, because we want to solve the problem recursively with one disk less here, right? And then we do the usual argument shuffling around, which is what this does here, right? So we shuffle the arguments around a little bit, and then we call Hanoi recursively, and then when that returns, we unwind the stack by using pop all as illustrated. So we have the old values from this incarnation of the recursive call back now in the registers, and we can now print out that move statement here, right? That we are moving the disk from source to destination, corresponding to that invocation, to that stack frame that we are currently in. And in order to put something on the display now, on the 6-digit 7-segment hex display of the microprocessor, we need to prepare a data region, basically a buffer in the memory, where we put in the bytes that we want to output, right? And then we can call a firmware routine which maps these bytes to the bit patterns that are required for the individual 7 segments to turn on and off, right? So there's a firmware routine for that does the conversion. But first we need to decide what we want to display. So we want to display the source pack, right? The target pack and the disk number, so that we can follow along what the program is doing. So we have source, target, and disk number memory locations here. There are labels here, right? There's a data region here for these 3 bytes, and we are setting this memory up, putting the current values from the registers there. So B has the source pack, right? And we put this into the memory there at that source address, right? And the same C has the target pack name and so on, and the accumulator has the disk number. So we are preparing this memory region, and then we are calling the routine which actually prints that now on the display. And since this is a firmware call, it also destroys the registers, so we're also going to save and restore the registers around that call. And let's see how call movement works. I mean, it's not super important because that is now using the firmware routines that the microprocessor has to offer in order to convert the bytes in our buffer region that we have set up, right, for source, target, and disk number into the bit patterns for the 7-segment display. And for that you need to set up the addresses here in the DE register. Is pointing to the first byte of your data region that you want to output. Then you also need another data region, which is the output buffer, which then contains the bit patterns basically for the 7-segment display, which are produced by that firmware call, right? Then you got to tell it how many bytes do you want to convert in that way, and then in the loop you use this firmware routine hex to 7-segment conversion, right, which sets the right bits for the individual bytes. And then we are just, once all of these 3 bytes and 3 bit patterns are prepared, we are actually calling a routine that then uses this prepared bit pattern in the output buffer here, right, and displays it for 250 milliseconds. So this is the delay in the B register. And scan 1 basically does the display of that bit pattern on the 7-segment display then, and then we return. So this is not very important, and that's also explained in the microprocessor manual, right, how you use the firmware routines for basic things like making a beep or reading from the keypad, or putting something on the display, right, like we did here. Okay, so we've then printed out here now the move instruction, right, how we are moving the disk from source to target, and now we have to make the second recursive call, and that's the same story like the first recursive call, right, and only we need to shuffle the arguments around a little bit differently from here, but else it's identical. And when that returns, we can also return from this recursive invocation of the Hanoi function. And if you look at the Rosetta code version online, you notice that this is already an optimized version. So the author here already performed tail recursion, basically meaning that for the second recursive call, he is not doing the push and pop basically to the stack, right? But so instead he's just using a jump basically, tail recursion optimization. But for the sake of clarity, I did not, put that optimization in here. I'm just using a proper, recursive call and proper return here. Yeah, so that's the program basically, and now all we have to do is compile this. So it's as easy as hitting the compile button, right? And no errors, everything successful and okay. And then you can see the listing here, right? Very nice. So you can also save these files. And so what we need now in order to program our microprocessor is the generated hex file. And I must say I struggled a little bit until I got the format right. So I'm going to show you here what you have to do in order to load this with PicoRAM 6116 then into the microprocessor. So let's copy and paste that here. And the first thing is the current reader does not support these address prefixes. So we are going to separate that out. And I already made a mistake here. Like this, right? So tricky stuff. The last line is also, not required. So you're going to remove all these. And actually after C9, basically, which is the last return, if we look at the listing, we can basically already omit everything here. But it's nice to have these zeros in the output buffer, because otherwise we might see garbage in addition to the converted bytes on the 7-segment display. So it's good to at least have this part in the hex file, right? So you see here are these a few zeros. So these are we are going to keep those. And then the last byte is always a checksum. So that took me a while to figure that out. So that needs to go as well. And then we can just write this basically as a using the file name, right? And then MPF basically is the extension that I'm using for this. Alright, so I copied the Hanoi MPF hex file to the SD card now, right? And so let's load it from there. So I called it Hanoi 2. Here we have the file browser of PicoRAM. And there's Hanoi 2, and hit OK, and then it's now loaded into bank 3, and the Pico is serving this program now, right? And so yeah, let's just start it at address 1800. There you go. One more run. Yeah, 7 steps, so it executed this for 3 disks as specified, right? And note that the halt LED came on now, so the program terminated. And let's actually increase the number of disks now. And so looking at the assembler listing, we see that at address 07 there is the n constant, right? So 3 here. At 1806 we have 3E, that is the opcode for load accumulator, and then at 1807 there's a constant 3, and we are just changing this with, say, 5, right? Okay, double check, yeah. At 1807 we have 5 now, and now let's start the program again, and that should keep it a little bit more busy. And we can just follow along, right? So here's the disk number that's being moved, and then this is the source pack, and that's the destination pack. And that's a version that does it fully automatically, right? Always waiting 250 milliseconds between you know, display updates. But I also implemented an iterative version that would allow you to play along basically with your stack of coins, right? And this program is already on SD card as well, and I called it Hanoi 1, right? Or actually the other program is Hanoi 2. This is just Hanoi. So let's load this one, and now I gotta push a button every time it moves the disk, right? And I think it starts with 2 disks now, so that's fairly straightforward. So let's start the program. So the first move is, you know, to move disk A, to move the disk 1 from A to B. Now it's waiting for a push of a button here. Then we are moving A to C, and then we are moving B to C, and then we are done for 2 disks, right? And again, we can also then increase the number of disks. To find the 3E instruction again. Okay, load accumulator, and here the value was 2, and let's, you know, load this with 3. Double check. Good. Let's run it again. Disk 1 from A to C, disk 2 from A to B, disk 1 from C to B, disk 3 from A to C, disk 1 from B to A, disk 2 from B to C, disk 1 from A to C, and done, right? Again, the hard LED came on. Alright guys, so yeah, if you want to make your own PicoRAM 6116 to take your Microprofessor software development experience and programming to the next level, right? Because then you can easily use your Mac and or PC assembler, right? And just put your assembler code, your hex file on the SD card, and you no longer need to type in anything in hex code using the monitor, right? Then go check out the GitHub repository, which contains everything you need in order to make your own PicoRAM 6116. Free of costs, right? I mean, only material costs, of course. Contains the firmware, the Gerber files, right, for PCB production, as well as the software. I also uploaded, you know, a folder, a zip archive containing demo programs, containing the programs we just looked at, including the Hanoi versions, the 2 versions we looked at as well. And PicoRAM 6116 also runs, works with the Microprofessor MPF-1B, right? So yeah, and it's actually configurable over an init file, you know, whether you run it on the 1B or 1+, and it also supports auto loading of programs, for example, right? So if I hit reset here, you can see that it is now loading, automatically loading programs into its 4 banks, right? So for example, there is the double die program here now, which I haven't demonstrated yet, which is basically, yeah, 2 die, right? Alright guys, yeah, thanks for watching, and until next time, right? Take care, bye.